Hi, my name is Marco Flowers, and I'm a third-year computer science major. This is my third year with AUVSI, and this year I was the project manager. During competition, I will be the judge liaison, and I'll also be monitoring the ground control station.
Hi, I'm Otto Yersch. I'm a second-year computer science major. This is my second year on the team. I'm a software team co-lead. During competition, I will be operating the path planner and other ground control systems.
Hi, my name is Matthew and I'm a second year computer engineering major. This is my second year on the team and I'm a software co-lead. During competition, I will be running the onboard computing system and the image recognition system.
I'm Winston Kwan and I'm a fourth year electrical engineering major. This is my fourth year on the team and I'm the embedded lead. During competition, I'll be part of the flight line.
Hi, I'm Michael Park, a fourth year computer science major. This is my second year on the team. I worked as part of the embedded team. During competition, I'll be monitoring the ground control station.
Hi, my name is Kevin Young and I am fourth year structural engineer. This is my second year on the team. I am the airframe co-lead. During the competition, I will be part of the flight line.
Hi, I'm Jessica Chan. I am a first year mechanical engineering major. This is my first year on the team. I am part of the airframe team. During competition, I will be on the flight line.
Hello, I'm Bachan Mono. I'm a third year computer science and bioinformatics student. This is my third year on the team and I serve as the safety pilot. During competition, I'll be maintaining control of the airplane in the event of emergency and taking control if the autopilot fails.
Our plane is comprised of 3 wing sections, the fuselage, tail, and cart. The wing sections are designed to be quickly detachable from the fuselage and disassembled to fit inside of a sedan trunk. We used a fixed high wing design for more ground clearance during belly landings. Belly landing the plane allows for a short landing distance and diverse landing capabilities. For the fuselage, our team used a composite wet layup of fiberglass reinforced with carbon fiber and core reinforcement to allow RF signals to pass through. We decided to use a folding propeller to reduce the chance of the propeller striking the ground upon belly landing. In addition, the motor brakes prior to landing, allowing the propellers to fold. We decided to use a cart instead of landing gear to reduce weight and drag. The cart allows for high ground clearance during takeoff. The front wheel is rudder controlled to steer the cart during takeoff. The plane can be quickly set up within 15 minutes and requires 5 minutes of service time between flights.
Our plane has a wingspan of 11 feet to allow for a low cruise speed relative to the weight of the plane of 22 pounds. This reduces motion blur. Fiber 1 can fly up to 40 minutes on a fully charged battery pack. The cruise speed is 33 miles per hour, the stall speed is 20 miles per hour, and the maximum speed is 56 miles per hour. We material tested donated high salt to ensure the shear strength of the adhesive and determined that it was usable for our purposes. We also tested the spar by performing a 3-point bend test by applying a 130-pound load and calculated a factor of safety of 6. In addition, we repeatedly dropped the fuselage from 3 feet, adding reinforcing bulkhead as a result of the test. Viper 1 has flown 14 flights, totaling 7 hours of flight time. It has flown in sustained wind speeds of at least 10 miles per hour as measured from the ground, but much higher in the air in addition to gust.
Our software system was designed to be modular, distributed, and performant. We created custom front-ends to streamline mission management tasks and to display information about the plane's location and status. Our 2 most important subsystems are our computer vision system and the path planner. The path planner generates flyable, obstacle-free paths around stationary and moving obstacles using Dubin's curves, while the computer vision system performs automatic detection, localization, and classification using convolutional neural networks and other algorithms. These systems are distributed across several computers and communicate through the hub, a publisher-subscriber messaging system that allows for our systems to easily pick which systems they communicate with. The plane uses a 2,050-watt brushless outrunner motor powering a 20-inch propeller. The motor is powered by an 8S2P 5,000 mAh lithium polymer battery pack. A separate 4S lithium battery powers the payload. The primary payload consists of the DSLR camera, the air delivery package, and the onboard computer. Other electronics include the Pixoc autopilot, servos, the gimbal motors, the RFD 900 radio, the RC receiver radio, and the Ubiquiti Wi-Fi radio.
This year, we plan on attempting all of the mission tasks. Based on our performance in mission tests, we believe that we have a high chance of success in autonomous flight, waypoint accuracy, static obstacle avoidance, manual image recognition, image localization, actionable intelligence, and emergent target tasks. We believe that we have a decent chance of success in automatic landing, moving obstacle avoidance, automatic image recognition, off-axis target, and air delivery tasks. Finally, we think that there is a low but high enough chance to make it worth attempting that we successfully achieve automatic takeoff.
We rigorously unit tested and integration tested our code to make sure it is performant and correct. In addition, we developed visualization tools to allow us to interpret our results and determine issues. For example, visualization of the path planner's return paths allowed us to determine what types of obstacle configurations that the path planner struggled with. We also developed tools to easily test our code via software-in-the-loop testing and with the judging server. Software-in-the-loop testing is very important as it allows us to test our code without risking a crash of the airframe. We can also take advantage of the speed up of the software-in-the-loop to run tests a lot quicker. To facilitate software-in-the-loop testing, we set up a software-in-the-loop simulator Docker container, abstracting away the installation process and making it easy for anyone to run the simulator. Over the course of 8 months, we have conducted a total of 20 autonomous flights. The average amount of time spent in manual mode per flight is 3 minutes per flight. Apart from autonomous flights, we flew the plane manually to set autopilot parameters specific to the airframe to ensure stable, consistent behavior during takeoff, waypoint navigation, and landing. The tuning process consists of initial calibration, PID tuning, total energy control system tuning, navigation tuning, takeoff and landing tuning. Between each stage, a verification flight is done to check if the tuned parameters yield desired flight behavior. Over the course of 18 semi-autonomous flights, we have collected the following waypoint statistics. With 123 attempted waypoints, we have hit 108, with an average waypoint miss error of 45 feet. Improving our waypoint accuracy and hit percentage involved tuning our plane to make it fly better, as well as improving our path planning systems to generate a flyable path. Our obstacle avoidance performance was tested in a variety of ways. We started by simply verifying that our algorithms consistently returned an obstacle-free path. We performed a series of tests against random waypoint and obstacle configurations, and our paths avoided 3,892 out of 4,820 static obstacles for an avoidance rate of about 80%. After these initial tests, we moved on to software-in-the-loop simulations. Over the course of these simulations, the simulated plane avoided 23 out of 28 stationary obstacles, giving us a success rate of 82%. Finally, over the course of our full mission tests, we avoided 8 out of the 9 obstacles that were a part of these tests. For dynamic obstacle avoidance, we believe that the combination of our static avoidance speed, our waypoint upload speed, and our obstacle prediction results give us a good chance of avoiding dynamic obstacles. After several tests, we have determined that we can upload 200 new waypoints to the plane in 2 seconds for an upload rate of about 0.01 seconds per waypoint. Our static avoidance algorithms are very fast, and after detecting an obstacle collision, we can generate an obstacle-free path at an average of about 0.2 seconds per obstacle in the field. Finally, our obstacle prediction algorithms are accurate within an average of about 25 feet, 5 seconds into the future. We believe that the combination of these factors gives us a decent chance of avoiding dynamic obstacles. Through the use of rapid prototyping, we were able to test a variety of different gimbal geometries until we achieved the best balance and stiffness. We also performed PID tuning until the gimbal was able to converge to its set point and respond to disturbances quickly. The imaging system has been tested in the air in a variety of different environments and lighting conditions to ensure robust performance. Environments include both grassy and barren environments, while lighting conditions include both sunny and severely overcast conditions during high noon and late afternoon. Different aperture, shutter, and ISO settings were tested before settling on using a small aperture with a high ISO and automatic shutter speed. The aperture priority causes a deep depth of field to ensure robust autofocusing on the camera. The high ISO ensures a fast shutter speed to minimize motion blur. The resolution achieved at 400 feet altitude with a 40mm lens is consistently 2 pixels per inch or 4 pixels per square inch. Each image covers 225 by 150 feet.
The imaging system is fault tolerant and reconnects automatically during flight. Since we perform salient object detection on the plane, crops of objects can be sent down to the ground station during flight, where manual recognition can be performed. Processing and images are distributed throughout the ground station computers for speed and to allow for multiple manual image operators. For automatic recognition, we achieved 68% accuracy for salient object detection on a dataset of 193 full-size images from previous competitions and test flights. We achieved 89% accuracy for junk filtering on a dataset of 400 crops of targets and non-targets. On a dataset of 112 targets, we achieved 50% on shape recognition, 47% on optical character recognition, and 62% on color classification. We localize targets by matching GPS data from the autopilot with time-stamped images and then geo-reference crops inside the larger full images. We tested localization of targets during test flights and were able to localize 52 out of 60 targets during testing, with the localized targets having an average localization error of 32 feet.
The airdrop was tested by dropping the water bottle from a 75-foot rooftop. We tested 8 times with 5 survivals. In addition, the water bottle was dropped from the backup plane from 250 feet. We tested 3 times with one that survived and landed 100 feet within the target region.
We conducted full mission tests to fully emulate competition conditions. We were able to complete 3 full mission tests with an average score of 60.7%. Some of the issues we had with the full mission tests were automatic takeoff not being fully tested in high wind conditions, and a crash of the primary aircraft before the tests, which did not allow us enough time to reintegrate our airdrop mechanism before the full mission tests. We were able to successfully hit all waypoints during the mission tests, along with avoiding 8 out of 9 static obstacles and recognizing 15 out of 18 targets. We expect to perform better than our average score, as before competition, the airdrop mechanism will be reintegrated into the platform, automatic takeoff will be better tested, and we expect incremental improvements to the rest of the system.